Hey, welcome back. Today we have a question. High-speed air jets strike the blades of the turbine rotor tangentially, while 1.5 meter diameter rotor rotates at 140 radian per second. There are 10 such 40 mm diameter jets. Calculate the maximum power output. The air density given is 2.4 kg per meter cubic. Neglect any lateral spreading. So the first, we need to analyze the question given. So what's the question asked? Calculate the maximum power output. Alright. So in this case, step number one, we need to draw the free body diagram or polygons of velocity vector. So here, let's say this is point number one and the outlet to be point number two. So step number one, draw free body diagram or polygons of velocity. So point number one, let's draw point 1. This is at the inlet to be V1, alright? So we draw the V1. So this is V1 in this way, in this direction. Okay, this is V1. And then this is VB. And then this VB is pointing to the right. So we can say this is the final going to the VB. Right? So this is VB. And then once the water entering this region, it will be in this direction because it follows the inlet of this vein in this direction. So in this direction, it will be in this direction. So this is the inlet of vein. So this we call as VR1 relative to this point 1. Okay, so the angle of V1 we refer to beta 1 here. So it is given that 30. So now we go to the point number 2. So which is at the outlet. So once the outlet, the relative velocity of outlet will be follow the deflector. So this is VR2 and here VR1. So how to draw it? First, we draw the VR2. Okay, this is VR2 in this direction. VR2 and then VB always horizontal. So the resultant will be at the middle here. How to get it? We do the we create the imaginary line like this. This is parallel to VR2 and then this is as well parallel to VB. So the cross section, we call this the overlap region here will be the resultant V2. So this is V2. Okay. So the angle of V2 from here we call as a beta 2. And then here the angle, we must know that the angle of vein inlet is alpha 1 and the vein outlet is alpha 2. So from here, okay, step number 2, we need to apply the velocity equation. Okay, the velocity vector equation. So V1 here, in order to get the V1 is equal to VR1 plus VB. Alright, we start from this coordinate and then in order to reach this point, we go to the other direction, VR1 plus VB, because this is the same arrow, so it is plus. And in order to get V2, which is VB plus VR2 or VR2 plus VB. So in other way, in general, we can say that V is equal to V relative plus VB. It's very simple, alright? In general, the same thing. So let's start with step number 3. Let's start with the point 1 at the entrance, alright? Entrance, which is point 1. So what do we have here? Point 1. Alright? Alright. So let's focus in the Y component. Right? In the entrance, we try to separate. This is in Y component, Y axis, and the other is X axis. So in order to get the V1Y, okay, let's draw this. Okay, in order to get V1Y, so this V1Y, okay, in order to get the V1Y, okay, let's say this is V1Y. V1Y is actually equal with VR1Y. Okay, V1Y, if we do the sign, it will be equal to VRY sine of it. Okay, so V, we use Y component first. V, okay, V1 is actually V1 sine beta 1 equal to VR1 sine alpha 1. Why this? Because take a look here. V1 sine beta 1, which is this one, V1 sine beta 1, we get this component in Y here that I draw. Alright, the next is we focus on this V relative 1. So V relative 1, we focus to the this vein angle, inlet angle, which is alpha 1. That's why we call as the sine alpha 1. Alright, this reflect to the VR1 reflect to alpha 1, V1 reflect to beta 1. So we must use VR1 sine alpha 1. Okay, and then here is for X component. Okay, V1, of course, cos beta 1. You can see here. In order to get the V1 X component, V1 cos beta 1 is actually equal to VR1 cos, okay, cos alpha 1. We will get until this one, because you see, this is VR, this is VR1. Once we do the cos, we only reach only this point. Okay, so this is VR1 X. In order to get VR1 X, we do the VR1 cos alpha 1. Alright, in order to get this one, and we need to plus VB because we have this component. We have to plus VB in order to reach this point. Okay, because this one V1 cos beta 1 will finally reach this one, so we have to plus VB. So V1 cos beta 1 is actually equal to, okay, V1 cos alpha 1 plus VB. Remember that in order to this V1 cos beta 1, this V1 cos beta 1 will reach this one. This one will reach this one. Will be like this. So in order to make it balance, so VR1x plus VB. So VR1x is equal to VR1 cos alpha 1, because alpha 1 related to the relative of velocity 1 plus VB. Okay, so from here, we need to substitute the value of V1 and beta 1, alpha 1. So we substitute the value of V1. So V1 is 200 given here. And given here VB. How to get the VB? This is velocity of the vane. We know that VB given here is there are 10 such while the turbine rotates tangentially while the 1.5 meter diameter rotor rotates at 140 radian per second. So let's say this is the rotor, this is the vane. Okay, so we only focus on this portion. However, this is rotate. Okay, rotate at 140 rad per second. And then this diameter is 1.5 meter. So the radius here is 0.7 meter. So in order to get the VB here, tangential here, VB equal to R of omega. Okay, so V equal to R omega. So radius 0.75 multiply with 140. Okay, so this on this part. Okay, let's substitute on this part. Alright, V1. Okay, step number 4, substitute only. V1 is equal to 200 sine. Okay, beta 1 here is 30 equal to VR1, which that we want to find out. We leave it VR1 sine alpha 1. Alpha 1 here. Okay, alpha 1 is actually not given. It's okay. Just leave it alpha 1. So how about this one? So V1, okay, we continue here, which is 200 cos beta 1 is 30 equal to, this is a this is a VR1. VR1 is equal to, that we need to find, it's okay, VR1 cos alpha 1 is not given, unknown, alpha 1 plus VB. VB here, remember, R omega. R here is 0.75. 0.75. Rotate at 140 radian per second. So just 140 radian per second. Alright, this is already in SI unit. So how to solve this? Right? Solve this simultaneously. So solve this simultaneously. So how to solve this? Alright, 200 sine 30. Use your calculator. 200 sine 30, you will get 100 equal to VR1 sine alpha. And this one you solve 200 cos 30, you will get 100. Okay. Okay, this one you will get 173.21 equal to VR1 cos alpha plus this one you solve it, you will get 0.75 multiply 140, you will get 105. Okay, simplify further this one, go to the other side, become minus. So 173.1 minus 105, you will get 68.21 PR1 cos alpha. So once you have this as equation 1 and you have this as equation 2, what to do? You can divide alright, equation 1 into equation 2. Alright, in order to make it this way. So you can divide this. So 100 PR1 sine alpha over 107 over equation 2, which is 68.21 PR2 cos alpha. Right? Remember that sine over cos is equal to tangent. So this this is BR1. Okay, this is alright. So this is BR1. BR1 we can cancel out. So only left sine alpha over cos alpha, which is tangent alpha. So finally you solve this. 100 divided with 68.21 equal to tangent. So alpha is equal to inverse tangent 100 over 68.21. So the final answer for the alpha is, you will get the alpha to be 55.7 degree. Okay, the angle of alpha is 55.7. So this one you will get 55.7 degree. Okay, once you get the alpha, and then it is easier for you to get the VR1. So let's use the equation 1. Okay, equation 1 is equation 1, which is 100 equal to 100 equal to VR1 sine alpha 1. So substitute alpha 1 to be 55.7. So VR1 equal to 100 divided with sine 55.7 degree. So you will get VR1 to be 121.05 meter per second. So that part is the VR1. Okay, we know that VR1 is actually equal to VR2. Okay, based on the Bernoulli equation. Okay, VR1 equal to VR2. So step number 4. Alright, step 4, we have discovered that VR1 is equal to 121.05 meter per second. Now we need to calculate for V2. Right, V2 and beta 2. This is not given here. So here, the beta 2 is not given, as you can see here. And then the V2 as well. We know that VR1 is equal to VR2 based on the Bernoulli principle. Okay. So now we go to the step 5. Again, we apply this one. Step 5, we apply this one, the same thing at the Y and the X axis. So step number 5, okay, apply polygon vector, velocity vector at exit point. Alright, so here we focus on, we have the Y component and X component. So let's take a look about the Y component, Y axis. So what's the Y axis here? So let's take a look of the polygon. The Y axis V2Y. Alright, V2Y, when we do the sine V2Y, in order to get V2Y is actually V2 sine, alright, V2 sine beta 2. And V2Y as well. This one we refer to velocity 2. How about we refer to velocity R2? So VR2 sine, we can sine using the relative angle, which is alpha 2. Okay, so this is actually the angle. From here is the 30 degree, which is alpha 2. So sine alpha 2 here is 30. So sine 30 degree. So we can equate this one. V2 sine beta 2 equal to VR2 sine 30. So V2 sine beta 2 equal, it is the same with VR2 sine alpha 2. Alpha 2 previously we discovered to be 30 degree. Okay, VR2. Okay, VR2 here VR2 here, we know that VR1 equal to VR2 because of Bernoulli. So VR2 we can replace with this one, VR1, which is 100, okay, 21.05 meter per second. So how about the x component? So this is x axis. So let's take a look about the x axis. Okay, so this is Vy, V2x. In order to get V2x, V2x only reach this point. When you do the x-axis, only reach this point. This is V2x, only reach from here to here. Alright, so V2y is actually equal to V2 cos beta 2, and then V2y as well. V2y, in other words, we can say that V2x, if we use this one, VR2 cos, which is angle here is alpha 2. Okay, we will get this point. Okay. So remember that this is in this direction. Alright, this is in this direction vector, it is negative. So this is negative. And then you need to plus VB here. Plus VB. Because VB going to the right. So it is plus VB. Then finally you will have the same magnitude. Alright, so this is actually V2x. Right, in order to, this is negative VR2, that means this is pointing to the left. In order to reverse, you go to reverse negative. This is VR2x, and then you have to plus VB. That's why it come out with this. Alright, so V2x, we write it down. V2x, V2x refer to, okay, V2 cos beta 2, okay, equal to negative, remember negative, VR2 cos alpha 2 plus VB. So in this case, we only need to find V2. So leave it, step number 6, substitute V2. Okay, substitute all the value here. So we don't have V2, we don't have beta 2 as well, but we have VR2 and alpha 2. Just substitute here. V2 is nothing, just replace V2. Okay, sin beta 2 is okay, not given. So VR1, VR2 equal to VR1, just substitute here. 121.05 sin 30. So you will get V2 sin beta 2 equal to, right, equal to 60.52. Let's say this is as equation number 3. Okay, and then we solve this one. V2 cos beta 2 equal to negative, this is not given, leave it there. Negative VR2 equal to VR1 as well, negative 121.05 cos alpha 2 given to be 30 plus VB. VB is V equal to R omega that previously we discovered. So VB is R omega. So R is 0.75, omega to be 140 radian per second. So you solve this, you will get V2 cos beta equal to 0.168. This to be equation number 4. So try to divide equation. Okay, divide equation 3 to 4, which is you will leave. So equation 3 is V2 sin beta 2 equal to 60.52. You divide both sides. this be 2 cos beta 2, this is beta 2, 0.168. Okay, 0.168. So V2 and V2 cancel, sine over cos tangent, beta 2 equal to, okay, you try to solve this one, you will get 60.52 over 0.168. You will get 300. Okay, you will get 360.24. So move tangent to the other side. You will get beta 2 inverse tangent 360.24. You will finally get the answer is 89.84 degree. So by using beta 2, substitute into equation 3. Okay, equation 3 is sub into equation of 3. So equation 3 is, we know that equation 3 is V2 sine beta 2 equal to 60.52. So move the other side, divide V2 equal to 60.52 over sine beta 2, which is 89.84 degree. So the final answer for V2 is 60.5 meter per second. Alright, now after we have gone through step number 6, we find out that the velocity V2 is equal to 60.5 meter per second, and then we need to apply the momentum equation at the horizontal axis, which is x-axis. So here, step number 7, which is apply momentum equation at x-axis. The reason behind this is because we need to find the reaction force at the x component so that we can input that force to the maximum work output, because the maximum work output relate directly to the reaction force at the x component. So in order to get the reaction force, we must apply the momentum equation, because the momentum can have the force component. So apply the momentum equation. Summation of force in x component going to the right is positive, is equal to mass flow rate multiply with V2x, this is x component, minus V1x. Alright, so here mass flow rate, we know that the mass flow rate formula is rho A multiply with V. If we use the velocity of 1, area we should consider of 1. So let's take a look of the area. It is given that the area of diameter jet here, we consider this jet is 40 millimeter, the diameter. So this is the diameter of water. This is the air jet. Remember, this is not the water, this is the medium of air. So since the air jet is 40 millimeter, the radius is 20 millimeter. So we are not using this 1.5 meter diameter of rotor. This consider this one. You can see the red color. So this jet, it is 40 millimeter diameter. Therefore, it is circular in shape. Therefore, we can directly apply to this equation of mass flow rate, alright, which is the density of air. We are using the air medium. So it is given that the density of air here is 2.4 kilogram per meter cubic. Just substitute the value in this equation. Alright, 2.4 is actually density multiply with the area, which is we use the pi r squared. So pi multiply with radius, which is 20, because the diameter is 40 mm. Definitely the radius is half from the diameter, which is 20 millimeter. So in this case, 1, 2, 3. So we convert to SI unit, it becomes 0.02 meter. Alright, so 0.02 meter squared. This is the area. And this is the density of air multiplied with velocity of 1. The velocity just going to the outlets of the jet. So it is given here. V1 is 200 meter per second. Alright. And then here we need to continue multiply with V2. The V2 previously we discovered to be 60.5. Alright. So 60.5, this is x component. So when we look at our polygon vector V2, in order to get the x component, we must cos with beta 2. Previously we discovered that our beta 2, alright, to be 89.84. So cos them, right, cos 89.84 minus with V1x, right? Our V1x here is 200. We look at the point 1, alright? V1 is 200. This is, we need to find this angle, alright? This angle, it is given that 30. This is beta 1, alright? So 200 cos 30, alright? Okay, this one we delete. So we continue here. 200. This is V1 cos 30 because this is angle reflect to the horizontal. Alright, this is velocity. So this is actually the whole is the mass flow rate. So using calculator, you will find out that the answer, alright, the answer for this is 100. You will find the answer of this is negative 104.3 Newton. Alright, remember that this is the summation of force. Do we have any forces in x component? So here we have the reaction force. The reaction force pointing this way. So definitely we have the reaction force pointing to the left, which is Rx, which is negative Rx. Alright. So just substitute here. There is only one force, which is negative Rx. So negative cancel out. You will get Rx finally equal to 104.3 Newton. Alright. After you find out that the reaction force in x component, then you can get the maximum power output from this equation, step number 8, which is power output equal to number of plate multiply with or number of jet nozzle multiply with reaction force in x component multiply with VB. Alright, this is body velocity of moving vanes. Alright, so number of jet here, and it is given that there are 10 number such diameter jet. So we have 10 of fixed air jet here. So 10 multiply with VB. VB we look at here. Alright, it is given to be in terms of radian. So 140 radian per second. Okay, in order to get VB. Okay. In order to get the VB, we know that the equation VB equal to R omega. Alright. So R is the radius. Alright, the radius of the rotor, which is in this case 1.5 divided with 2 multiply with omega, which is 140 radian per second. So in this case, N is 10 multiply with Rx is 104.3 multiply with VB, which is R omega. So radius is 0.75 multiply with 140 radian per second. So finally you will get the answer is 109,600 watt. Right? So you can simplify 109.6 kilowatt. Therefore that is the final answer.